This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Robert Blumen. I am here at QCon San Francisco 2016 with Gil Tene. Gil is the CTO and co-founder of Azul. He's worked with Java and virtual machine technologies for over 20 years, pioneered Azul's C4 garbage collector and other runtime technologies. He is a member of the JCP Executive Committee and in 2006 was named one of the top 50 agenda setters in the tech industry by Silicon.com. Gil, welcome to Software Engineering Radio.
Hi, thanks for having me.
I also wish to thank InfoQ, the organizers of QCon, for kindly providing the room where we're making this recording. And at QCon, Gil is giving two talks this week, one Java SE State of the Union and the other Understanding Hardware Transactional Memory. So Gil, would you like to tell the listeners anything more about yourself?
I think introduction-wise, that's pretty good, but that's sort of the dry bio stuff. In general, I like to think of myself as an engineer, a software developer, and I've been playing with and building things for over 30 years, ever since VAX 11, 780s, and the first PCs were around all the way to today. I've gotten to build software at almost any layer, operating systems, device drivers, embedded systems, full-blown application servers, applications, and now for the last decade in some virtual machines, JIT compilers, garbage collectors, cool things that kind of do the hard work. And I've also programmed in lots of languages. So I like to say that I've made a lot of mistakes and have learned from a few of them. And, a lot of what I end up talking about in some cases is kind of the lessons learned and things that I see people repeatedly doing that I also used to do and what we might be able to do different about them.
I hope today we can benefit from some of your lessons learned about tail latency. Before we go into tail latency, could you define what is latency?
Latency as a term actually has a fairly okay definition. Latency is a reaction time. It's the time from when one event happened until some other event that results from it happens. It's not unique to software or computers. For example, a chemical mixture has a latency of reacting to putting something into it. But when we talk about latency when we talk about applications or networks, we usually mean the time it takes from some input until some output happens, from a request until a response arrives, from a user click until they see stuff on the screen, or from a message entering a system until something happening at the other end of that same system, not necessarily to the same point. When you translate or look at more queuing theory terms, rather than look at latency as a term, I usually like to actually separate the parts. And observability, you have the response time, which is the externally measured time from when you do something until whatever impact happens. And in queuing theory, that is broken usually into a service time and a wait time. The service time is how long it took for the thing that you were doing to actually happen. And the wait time is how long you were waiting until it started to happen or after it happened and before you saw the indication. So you can think of a time in a queue versus the time to actually do the service. I think the important thing when people look at those is that the only actual observable or externally observable thing about that is the response time. The internal times are actually not externally observable, but their dynamic actually affects behavior. So when you're modeling things, knowing the difference between service time and queue time and length matters.
I'm a user and I'm trying to download a web page or an image. what I perceive is the sum of all the service and wait times.
Yes.
Okay.
And response time is the sum of wait time and service time.
Okay. I found an article when I was reading up about this called How 1 Second Cost Amazon $1.6 billion in Sales. From this article, it says Amazon calculated that a page load slowdown of just 1 second could cost it $1.6 billion in sales each year. Google has calculated that by slowing its search results by just 0.4 of a second, they could lose 8 million searches per day. Can you explain how can what sounds like quite small degradations in latency have such huge economic impact on a business?
So I'd look at it in two parts. One is the direct question you asked of how does that latency behavior impact the business and why is it so big? But the other part is when I look at summaries like these, I unfortunately think of them as they're fairly simplistic. So for example, if you read the 1 second slowdown of a web page, well, does that mean one person saw 1 second slower response time? Did everybody see 1 second? Was it that the average was 1 second longer? Which is it? And usually there's no good description or answer. Same for the Google and Amazon description. Those usually happen because if you take what the people who actually did the technical work do and follow it all the way to some written article somewhere said it, it got censored and simplified and dumbed down on the way.
The Forbes magazine writer didn't
Yeah.
know those details.
Like I'm almost willing to bet that this is not that the average, if you change the average length of a page by that amount, that is the effect. I do believe that some change in length to some of the pages has those kind of effects, but in our experience, it is tail latency, a lot more than average latency, that has an impact on things like revenue. So to the actual question you asked of how come something so small has a huge effect on revenue, we could talk about an example sector that we, for some reason, ended up working in a lot, online shopping for clothes. Amazon does online shopping for lots of things, but we found actually that for some reason, clothes shopping likes our product. And it took us a while to figure out that that's a sector. It turns out that these days when people shop for clothes, you actually go through a shopping experience, and it tries to give you an experience that's somewhat similar to shopping for clothes normally. So it's not a dry, let's read about this TV or toaster, pick the model I want, and then go look for a good price on it. It's literally a shopping and browsing experience, and it tends to be very interactive. In fact, I think that the only thing more interactive or where interactivity and responsiveness is more critical to it online is gaming. Gaming is obviously very sensitive to glitches and late jitter, whatever it is, but online shopping is too. And the question there is, how would a tiny bit of difference in responsiveness, why would one image out of 100 being slightly slower affect revenue? The answers to that are that if you make the experience itself become disappointing, annoying, laggy, whatever it is, you create opportunities for people to just change their minds. Changing their minds may just be they got distracted by something, or it may be that they thought too hard and decided not to buy that shirt that they just bought in the shopping basket. Maybe it's not a good idea and they had a chance to think about it. Or it could be just that this is too much bother. I need to look through 50 or 100 things and it just takes too long. I'm not going to do it. I'll go to a competitor's site where it runs smoother. Those seem to have very real impact. So tiny changes to the responsiveness, reactiveness, and the design of pages have a huge impact on the revenue that can be extracted from the exact same traffic that arrives at the website.
Use the term tail latency, which I want to focus on. If I have 1,000 requests and I know the total wait time for each request, I could look at average, standard deviation, 50th percentile. How do you define tail latency, and why do you consider that the most important measure?
So I actually don't really define it or use it as a term as much. When people talk about tail latency, they usually refer to the higher percentiles. Higher could be 99, 99.9, maybe 5 nines, all the way to the maximum. It's not the main part of where most things are. So think of it as rare events that happen to be longer than the rest. And the assumption, when we talk about tail latency, it's always in a percentile term. So take all the response times you had, sort them, and you're looking at the worst ones. So the 1% worst ones, or the 1 in 1,000 worst ones, whatever that happened. That's the tail. And the reason I think people talk about tail latency is because usually if you don't say tail latency, they'll tend to talk about the center or the median or the average or the common case. The reason the tails are much more important than the common case is because humans do not perceive a common case. Humans do not forgive you because your average is good. Humans do not think of things as, I ate a bag of peanuts and on the average they were tasty. That one bad peanut, that's what they remember, right? Pain is what you remember. Bad experience is what you remember. If you go to a restaurant and you like the food there, and you go there every week and they give you bad food, you're probably not coming back. Or maybe you'll come back if you're really loyal and you give them one more chance. But 2 out of 1,000 and they've lost your business. And that's the actual reaction. That's the perception of quality and response is not an average or a common. It's how bad is it.
Let's go to that example of the shopper who might want to look at 50 shirts before they pick one. Do you have either some data or based on your experience, where do humans start to perceive a site as being slow? Is it 90 percentile, 99?
So first of all, humans perceive the worst case. They don't perceive any percentiles. If you ask somebody, how did the website respond? Whatever the worst thing they saw, that's what they'll answer with. Yeah, if you've been using it for a whole week and it only did the little circle thing one time, maybe don't forget about that one. But if you sit there and you're using the website and you're looking at 100 shirts in 3 minutes, it's the slowest shirt. It's not the fastest shirt, that's for sure. Nobody cares how fastest was. Nobody cares what the average is. Nobody cares that most of the time you give them good stuff. They just care that you slow them down. And that's true for pretty much anything that's a human experience. Now, beyond human experience, there are other places where latency matters, not just from a perception point of view. And that has to do with, requirements of reliability or risk. If you're in a trading system and you're making a bet because the market conditions are a certain level and you're going to do some trade that makes money, assuming the market conditions don't change, then if the market conditions change, there's a risk that you lose a lot of money. And the longer the latency, the longer the risk is. It's enough for there to be 1 in a million chance of something that happens that costs you 1 million times more to completely offset all your profits. So it's a risk-reward, risk-cost computation of it. And similarly, you'll find it in other systems where if you look at common modern microservice architectures, for example, a normal way to design microservices so that failures do not cascade and bring down your entire infrastructure to prevent services from overwhelming other services.
So just to wrap up what you were saying then, maybe in retail, once per hour, once per day is too much, whatever that translates into, but once a week would be acceptable, whereas in the trading system you described, even 1 out of 1 million latency spikes might be out of requirements for that system.
Yeah, those are not, I wouldn't use those as specific for the sector. It could be 1 over 1,000, it's that rare events matter.
Yes.
To question about the human perception parts, I think that humans perceive high tens of milliseconds to low hundreds of milliseconds. There's definitely the ability to differentiate those. These days, and this has changed in the trends over the years, snappy website responsiveness is in the order of 100 milliseconds. If you want to try and think of it for yourself, think of typing into an autocomplete field for a search. And what kind of lag would you accept before the next autocomplete shows up before you think this is laggy?
Sure.
That is in the level of 100, 200 milliseconds at most today, where if you go back 5-10 years ago, people would have easily accepted a second as acceptable because they weren't autocompleting.
We're talking about a latency of hitting a single endpoint. Modern web pages, you might be running JavaScript that's hitting 100 endpoints to show you the page. all those endpoints are going to have different latency characteristics. What does the user perceive on a complex modern web page as responsive?
So the answer to that is probably complicated. It has to do as much with the design of the page as anything else. But if we put aside the design of the page, suppose the actual information that you are presented with is what we're talking about, not the auxiliary unnecessary information we might want to show you, but it's okay if you don't see, right? So in a shopping scenario, I just popped up stuff and I'm going to look at 30 shirts. When do I see the 30 shirts? Not patchy, and some of them are not here, but when do I have the set to consider and browse through? And remember, since this is supposed to feel like shopping, until they all show up, you don't bother to look at the rest. So it's all of them. It's the set of information we're trying to show. And if those 30 things involve, say, 50 or 100 separate HTTP requests, whether they're to the same server or different servers, doesn't matter. The human will say, my click is complete when the data is in front of them, when it stopped moving, when they can actually start contemplating and reading it. And there's a lot of interesting tricks that are done in web design to try and get you to that point before everything has been delivered. And that's the design of the page. Maybe you could start reading the article before the ad has showed up and it won't reformat your page. But if you start reading and the shape of the page changes because an ad showed up, you consider that annoying. In fact, you would rather not even start reading if somebody's going to change the shape of the page after you start. So that's bad behavior. So I actually like to highlight the difference between the perceived response time of the consumer, which is a human in this case, or maybe a service that made a request, and the set of individual operations that came into producing that. So if you click on a web page and 97 requests go out, 97 responses come back in, and you see the information, then one of my response times involves 97 other response times. And my worst response time, or my response time, will be the worst of the 97.
Okay, so I'm going to give an example that's a bit dumbed down, but it's because I can do the math in my head right now. But if I'm going to view 100 shirts and each one is going to make 10 API calls, I'm making 1,000 API calls. And if I know 1 out of 1,000 of them is going to take a second, the page is going to take a second.
Yes,
and,
that's a good rough way to think about it. If you actually look at it from a probability perspective, it doesn't mean that every page will take a second. It means that there's a 1 in 1,000 to the power of 1,000 chance, right?
Yes.
It's a dependent probability thing. So there are some pages that will not see this, and there's some pages that will see more than one of this. But without knowing any correlative things, if 1 in 1,000 things go bad and you do 1,000 things, then most of the pages you do, or the vast majority of the pages you're looking at, will have the bad thing in it. That's a good explanation or example of how something that would be considered the tail latency to one thing, the HTTP response time, is by no means the tail latency to the human. The median latency the human will see will be the 99.9 percentile of the HTTP requests, because there's 1,000 requests on each page. So a tail to one thing may be a common case to the other thing.
So I can't do this math in my head right now, but if you think a user is going to visit your site every day for a week, and you're willing to let them have one bad page view a week, and each time they visit your site, they view 10 pages, and each page is 1,000 API calls, then the level you need to meet your requirement is quite high.
Yeah,
I can't do all the multiplication.
Yeah, and it's probably one you can't afford. The good news is people are forgiving enough that once a week a slow page is not going to make them think you're slow, and they're probably going to blame Comcast instead of you for it. But if you systemically are slower than another site, they're going to know. I also don't do the math as fast as needed for that, but I have actually computed examples. So for example, if you look at a session, so think of during a session, not a week, but one session of interaction, what's the chance of seeing a certain behavior? And we say a session is 5 clicks, and each click involves only 40 resources. This is a dramatically smaller number than reality. Most pages are a lot more than 40 resources, more sessions are much longer than 5 clicks. Let's assume it's that short of an interaction. mobile applications might be in that space where you're talking about that short of an interaction and only fewer resources. That means a total of 200 things we get. And the interesting questions to ask are, for example, how many of the people that do this will see something worse than the 95th percentile? This is something I've actually done the math on.
Okay.
So the number of people that will see better, will not see worse. So the number of people that will not see anything worse than my 95th percentile when they're doing 200 different operations, that's 0.003%. Or more specifically, it means that 99.997% of people doing this will see something worse than the 95th percentile of the individual operation. But that's a good example of showing that the 95th percentile of an operation that you do a lot of is usually an irrelevant thing if you're trying to determine any kind of reasonable part of your population. Only a tiny sliver of the people involved will ever stay below that number. And all you know is that pretty much everybody else, 99.997% of people, are seeing worse than this, but we don't know how much worse. Which is why you generally need to keep more than the 95th percentile or the 99th percentile, because people will see that.
Due to all the multiplication of how many experiences times objects times API calls.
Yes. Yeah. You can simply think about it, if what you show me involves 100 things, then you need two more nines you need to look two more nines deep into the thing than what you want me to do. If you want my 99% to be good, then the 99.99 percentile of the thing I do 100 times needs to be good. That's kind of intuitive. Another reverse way of looking at that question is, suppose I wanted to know what the 95th percentile person would experience. Like what 95% of people will see that or better. I probably need to look at the 99.9 something percent of responses, as that's the number that 95% of people will experience better. Because of those order of magnitudes multiplication of how many times you do things.
Means the problem is even much harder than we had hoped.
Yes. The way this translates into sad reality is when we look at things that monitor servers, components of systems, parts and services and microservices, the percentiles that we care about in those should be a lot more nines than what we care about with the people, because usually one human interaction involves more than one database call. So looking at the 99 percentile of a database only tells you what everybody's going to see worse than. It doesn't tell you anything about what the likelihood of them seeing other things are.
For building a distributed system where requests run in serial through a bunch of components and over networks, I think what you were just explaining about how response times aggregate in the browser also explains how responses aggregate through multiple steps in serial. Is that correct?
Yes. In fact, if we look at most things, there's some combination of parallel and serial. It's kind of like a tree. So there's some serial paths down the tree. So even if you need to do three things and you can shoot all of them off at the same time, each of those three things may be serially waiting for some other things to happen. So, for example, you're being asked to look up an item in a product catalog. The logic of the server that does that sees your request, parses it, and then figures out that it needs to perform a database request. So it goes to a database and does the request. And that database figures out that this thing is on disk, so it goes to a disk and asks for a sector. Each one of those is an example of a serial operation that will not complete until another serial operation completes. In modeling these, you can actually look at this as a sequence of response times and service times that are nested. So the response time of one thing is the service time of another thing. So if I'm the database, and I ask the disk for something, then the response time of the disk is my service time. But the question I ask the disk may be alone and it goes and gets it right away, or maybe there's 100 deep queue of requests in the disks that have been there for other reasons, and I'm waiting in the line for 100 other things to complete before the disk even considers my request. So the response time from the disk is longer, and the service time in the disk is short. But what I see as a database is just a response of the disk. Similarly, the thing that asks the database has a similar, whatever the response time of the database is the service time of the things that asked it, all the way up to the outermost response time of whoever initiated. So at each level, if you have these composed services that are nested, then what is the external response time, there's some wait time and service time that's component of that. The service time is comprised of response times that internally have wait times and response times.
Okay, so you mentioned then you said the wait times are typically time spent in queues. What are some of the different kinds of queues that exist in a typical system?
So queues and wait time are not necessarily the queue you would think of as a data structure. So the wait time functionally is the time from when you wanted the service to happen until the service started to do its work. Between the two, you waited. And technically, you're waiting in some queue somewhere. Now, it could be that your request arrived at the thing that does the work, and it's got some resource that is serialized, so you're waiting in a queue. Or maybe it just arrived in the socket, but nobody's read it yet, and the socket is a queue. Or maybe it didn't even arrive there. It's still sitting in your socket because back pressure has made it not sent. Or maybe even you couldn't even make the send call on your software because of the previous one is blocked and you've backed off. You could be anywhere in the chain between wanting to do the thing at the time you wanted to and the service actually starting to work. Anywhere in that chain is a wait, and those queues could be any spot, anything where this will eventually happen but is not yet started would be a queue.
So I'm aware, for example, that in a spinning hard drive that has one head to read the platter, that all the requests to read and write are ultimately serialized to that one head. So would that be one example?
Yes, that would be a good example. But then if you look at the different protocols you talk to disks with, some protocols will allow you to post multiple requests. You can post the next request before you get the next one, and then there's a queue inside the disk logic that is holding a request. And some of them will say, until I respond, you don't give me another one. And then the queue is going to be on your side. And the reality is probably a combination of the two.
Another source of latency tales that you're very well informed about is garbage collection. How does garbage collection introduce variability into the latency of an application?
So garbage collection, or more specifically garbage collection pauses, are an unfortunate side effect of how some managed runtimes manage memory, where as they need to perform the action of garbage collection, they will freeze the entire application until some phase is complete. And when that happens, if that takes some perceivable amount of time, or if that is a dominant reason for a stall or a pause, then that tends to be the thing that makes waiting happen, the thing that makes queuing accumulate, the thing that makes the service that you are waiting to start not yet start. So garbage collection pauses are a dominant cause for that in garbage collected systems. But those pauses are no different in behavior or functionality than other reasons for stalls or pauses. So the simplest one I like to tell people to think about is you can always go to a server and hit Control-Z and stall your process. That is a pause until you let go again. A garbage collection pause is no different than that, except that it does it when it wants to. A loss of your scheduling quantum on a CPU where you've been running for a while and now it's somebody else's turn, and you'll get CPU again 10 milliseconds later. That's a 10 millisecond stall that again is no different than a pause that happened with one of a Control-Z or GC pause. There are many other causes like interrupts and power savings modes and stalling for disk and I/O. Many things could cause you to stall. When you work in the field and you look to improve these, you tend to make educated guesses about which dominant ones are likely and try and reduce them. So, when you're running Java or Python or JavaScript, then it is very likely that garbage collection pauses are one of the dominant factors in hiccups, stalls, whatever we call those things. And those will invariably show up as tail latency numbers that are very high, that are orders of magnitude higher than the typical or average. So while your average or your typical might be 7 millisecond response, you might occasionally get a half second response.
So I'd like to think about this problem of I'm trying to design a system, a retail system with certain latency characteristics, and I could see a couple of ways to come at it. But let's say the first way is I'm going to try to control the latency of all the components and get it down in the range I want. I took queuing theory in school, and we had these graphs where as you put more throughput through a system that you see latency increasing. So what are we looking at when we see that graph? What is is that a real description of reality, or does that leave something out?
So I actually think there are ranges to the response there. If you take a system and you saturate it, meaning you ask it to do work at the rate it can do the work or a little more, then your queues are always going to be full. There's always a full line. You're basically doing things as fast as you can, which fundamentally means that the response time measured from the outside will be your service time plus the deepest queue you have. It'll be long. If you have room for 1,000 things in the queue, there'll be 1,000 things in the queue because you're saturated. So at that edge of the system where you've saturated it, response time will always be terrible. It's almost irrelevant to measure how bad it is because it's theoretically infinite. Right?
Couldn't do any worse.
I mean, if it could do 1,000 things a second and I ask it to do 2,000 things a second, what actually happens is the line gets longer by 1,000 things each second. The longer the run is, the longer the response time. Right? It's just the line keeps getting longer and longer. And even when I finish the test, there could be a million more things to do. So fundamentally, at saturation or post-saturation, response time is actually an irrelevant behavior. It's not a metric that matters. Now, what happens before saturation is interesting, and there's this obvious other end of the spectrum of at idle. When there's no work being done and you're just doing one operation, there's nothing in the queues. You're basically measuring the service time of the system because you're not waiting anywhere. And that's a nice, happy area. And there's this question of how do things behave between this idle point and the saturation point. That has a lot to do with questions of arrival times and consistency of execution. If you had a perfect arrival time, let's say I can do 1,000 things a second, and I'm only asking for 100 things a second, but beyond just saying that it's 100 things a second, it will be 100 things a second spaced out 10 milliseconds apart.
I see. So if you could do 1,000 things per second and 1,000 requests arrive all at once, it will still take you time to work through all of them.
It'll take me a second to get the last one. But if there's 1,000 things arrive one every millisecond, each one will only take a millisecond.
At the same rate you can do them. Yeah. Got it.
So an interesting observation is when people talk about rates per second, there's an implicit assumption that we don't care about response times below a second. Because if we did, we wouldn't be talking about 1,000 a second, we'd be talking about 1 per millisecond. So suppose if what you care about is, I want to make sure things are below 10 millisecond response time, can you do that at 1,000 a second? The answer is, I don't know, because you didn't tell me if the 1,000 arrive in the same millisecond or not.
You might get the 1,000, wait a second, and then all 1,000 are done, and all of them took a second. Right. Okay.
But if what you told me is, I need to get the answers in 10 milliseconds or less, and then my question would be, so how many messages will give me in 10 milliseconds? As long as it's less than I can perform in 10 milliseconds, I'm good with that. So really the rate per time unit should be of the scale of response time we care about. So when we look at databases where we want response time to be in milliseconds or low tens of milliseconds, our actual mindset should be how many messages per 10 milliseconds rather than how many per second. Obviously, people normally talk in per second messages, but the distribution of arrival time is important. So that's one part of the modeling that is hard. If you actually look at actual arrival time in real systems, it is nowhere near nicely spread evenly. So you can try for rules of thumb. You could say, assume that within a second, the instantaneous rate is 5x the per second rate. It highly depends on the domain and the use case. But the instantaneous arrival time in a fraction of a second is more important than the rate per second. One of the interesting observations I've seen is in mechanized systems like financial services systems, there tend to be a much higher natural concentration of arrivals than in things that are humans interacting with systems. So for example, in a trading system, usually there's some sort of information ticker going around the world, like Reuters, that ticks 4 times a second. And every time Reuters provides new information, some algorithms will decide to perform some trades very quickly after, which means that if you look within a second, you see spikes of arrival 4 times a second. They're not evenly spread. There's just a lot here and then a lot there and a lot there. Yeah, there's stuff in the middle, but there's a very, very high spike of arrival, probably a lot more than 5x the typical. That's because there's some universal clock everybody's ticking to. It's synchronized in time and everybody acts on it. Luckily, humans don't work that way. We don't have that accurate clock which synchronizes all of our clicks to happen at the same millisecond of a second. So when humans are interacting with systems, you tend to have much better smear going on. The interesting artifacts that you'll see if you study arrival times deep inside some systems, though, is that sometimes you'll see human interaction that seems to arrive in spikes during the second. And the reason that happens is that some system in the middle was doing polling and batching work. It didn't immediately react. It said, let's gather all the stuff you do in the last 10 milliseconds and then do it. And by doing it, it created these clocks. And it's not the batching that did it, it's the fact that the batching happens on the same clock everywhere. So they start aligning. And you get these things that you would think are random, but actually arrive in spikes. That's not a bad thing, it's just an interesting observation of distribution there. So arrival is one key thing, right? You need to design for the peak arrival time within the response time you care rather than some average.
Okay, so it's not enough. I'm going to build this online store and I'm going to engineer it for page loads within 500 milliseconds. You still need to tell me what the arrival rate is that will sustain that load time.
Right. So yeah, if you want 500 millisecond response times, then you need to know how much can arrive in 500 milliseconds.
Yeah.
If you want 50 milliseconds, you need that. The other end of the same, that's the arrival time itself. Only hypothetical systems consistently execute and respond at the same time all the time. Things happen to systems all the time, whether it's interrupts or context switches and scheduling or page faults or garbage collectors or power saving modes.
You're running on a cloud in a virtual machine.
And your neighbor ate up some time. There are things that even though the averages will be good, will disrupt your individual operations and make them longer or shorter. Every time you have a disruption that even momentarily makes you fall behind, not only the operation you did takes longer, but a queue builds up. So if I didn't get any CPU time to work on things for the last 20 milliseconds, and you are sending 1,000 things a second at a perfectly even rate, I have a 20 entry queue now to deal with, and I have to draw it down. But things are still arriving, which means it will take me time to draw it down. So the queues and the spikes that arrive as a result of momentarily slowing down has a drawdown effect and additional tail.
There's a lot of thought gone into building reliable systems out of unreliable pieces. We know that instances on the cloud fail and come and go. Every type of device in our network and hardware fails, yet we can build reliable systems that far exceed the reliability of any individual component. Now, is there a similar thinking process around latency where I can't get rid of queues, I can't get rid of work building up at different places in the system? I'm dealing with hard drives that are going to sometimes take an extra 500 milliseconds to do a read. How can I engineer an entire system with predictable latency out of pieces that have variable latency?
I don't like the term predictable latency because most people that deal with it don't deliver it. So, for example, we do not deliver bound latency in the practical term in commercial systems. Hard real-time systems, hard pacers, that kind of stuff probably we do. But in most of the cases, we're looking to shape the latency behavior, including the tails and high percentiles, to fit within limits. So we want the 99.9 percentile to be below X and all those, even though the components we have are worse than that. Now, there are multiple ways people could go about delivering that. You can go to sort of the ultimate, more complex, not super practical to build the entire system out of, but very useful things like systems that perform the same thing down redundant paths at the same time, and it's enough for one of the paths to complete for you to actually continue the work without even waiting for the other paths to complete. Those kind of idempotent designs where you do something and you're going to get the same result, even if you do it 3 times, are great, but they're also very hard to design well in a large system. So you might find components that work like that, or things like work that where it's enough for 1 or 2 things to be alive and respond, and you take the first response and run with it. And for example, systems like Zookeeper will work on a quorum-based protocol where enough arrival is enough to move forward. So even if you have laggards, whether they failed or just come in late, it doesn't matter. But most systems are not built that way. Most systems get complex enough that it's really hard to achieve the state consistency promises needed to do this. So instead what you do is you work around detected failures. The simplest way to do that is a timeout and retry. You need something, I need to respond in less than a second. I'm not going to wait a whole second. I'll wait 50 milliseconds. You to give me an answer, I'm going to ask it again and again and again. Now suppose the thing that you asked has a 99 percentile of 50 milliseconds. That means 1% of things are not going to come back. But those 1% are going to get retried, and 99% of those will come back. So my 4 nines is 100 milliseconds. My 6 nines is 150 milliseconds. And that part of the operation is now at a 6 nines of 150 milliseconds, which might satisfy what I need for the end result. And I could put a bunch of these together and get them. So the basic mechanism of a timeout, a short timeout, and a retry mechanisms, where you work into the system the fact that you might retry 2-3 times before you get the answer. You need enough time to do that, is a good way to work around relatively unreliable response time and retry. That also tends to work well for both situations where the thing you're waiting for the answer answered but not quickly enough, or that it actually failed. And you just went and got the answer from somebody else.
If we push that concept to one more level downstream, could I make a request, say, here's what I need. I need it in 50 milliseconds or less. And if you've worked on it for 50 milliseconds, you don't have the answer, just give up because I'm going to go get it somewhere else.
So this is where the circuit breaker concept starts coming in. The problem that happens when you build simple timeout retry mechanisms is that if you have actual failure, that's actually pretty good. So if something failed, you just, it's not affected. But the effect you get from timeouts and retries is that you're generating more requests for the same work that you needed. And you can end up taking a system that's now slow because it's under load. It's been slowed down. It takes longer than the timeout to produce a result. It does produce the result, but by the time it gave the result, you gave up and then asked again, producing more work, slowing it more down, and then it kind of goes downhill from there and snowballs. The way to prevent these kind of cascaded system effects, and they happen at many levels, way beyond just one step, is to try to react to timeouts as a very bad thing that makes you not even try for a while. So I think of it as kind of a violent reaction to failure, where what you're actually saying is, since I failed, I can try and push harder, but rather than push harder to induce failure, I will ease up. I'll fail quickly. So whenever you have the option, you say, you know what, I just don't have the answer to this. And by doing that, you've saved the system that was misbehaving from additional pressure. And circuit breakers fundamentally are things that attempt to react to bad performance, bad behavior, bad reliability by easing up the pressure rather than pushing harder. Hoping that ease up will allow the system to either catch up or work to its parameters. It's a form of flow control where, hey, I'm not doing well. Don't you make me do even more work, right?
So this is a way of limiting the operating range of the system so that you get the latency you want for those requests that you're able to serve and not taking on more requests than that.
Yes, but fundamentally doing that requires pushing back. And that pushback often means accepting that something won't happen. Now, there are many applications in the world where that's very acceptable. There's some that are not, but if you look at things like serving ads or putting up recommendations or even auto-completing your typing, if every once in a while it didn't happen, it's not terrible. You had to put in one more letter before you got it autocomplete. You wouldn't know. If the ad that nobody sold you anything, well, we could have made some money, but all we did is lose an opportunity. Didn't give you a bad impression. So, for example, I have this room, I could put an ad. If I can't figure out what ad to put you, I'll just put a baked image there that I don't have to think about. I don't have to figure out that you've gone hiking recently and maybe want to buy a tent. I just show a stock image, right? You don't really know the difference. And I just lost an opportunity. So there are many things where you can actually go back to the application, the value the application tries to provide, and push back on that. Say, is it okay if we sometimes just don't do this? If we don't do the smart thing, we do a dumb thing instead because we couldn't do the smart thing fast enough. As long as I do the smart thing 99% of the time, 99.9% of the time, probably okay. And those kind of things basically react where circuit breakers don't attempt to actually get the answer. They get a cheaper answer, a worse answer, and move on.
From a business standpoint, then, let's come back to this example of building the store. You could say, I can't guarantee that I'm going to show you all 30 shirts with all the chrome in less than 500 milliseconds, but I'm going to show you some shirts in less than 500 milliseconds, the ones that I could get back.
Right.
From a business standpoint, is that sometimes better? Say, I'm going to show you what I've got in reasonable amount of time and make you wait to see everything.
I think that's a subjective, specific question. Sometimes yes, sometimes no. So I think there are a lot of cases when the answer is yes, especially when what you are doing now will never be repeated. But there are many places where the answer is no, and I think shopping is actually one of the examples where the answer is no. When people browse to shop, they usually don't immediately choose and buy something that they found. And if you actually look at the patterns that people go through, they'll go look around and they'll come back, which means that they expect to get the same answer the next time, or they won't know where to find the thing that they want to go back to, right? It's lost. Somebody shuffled all the clothes on them, which is why in that specific example, you actually want to repeat the same answers you gave the person before. So you can't just do a best effort and then later do a better one. What they need to see is the same thing, like, oh, I remember that I had the cool thing over there. I think I went here and here and here to see it. And if they go here and here to see it, they need to see it. So that's an example where if you expect like what you see, you expect to have some sort of it'll still be there tomorrow or today or in an hour and a click, then you can't just do the best you can for that part and do the best you can again. Although at extremes, maybe it's okay. But there's certainly a lot of places where that's not the case, where the experience you're going through now will never be seen again. Ads are a perfect example. Nobody expects to see the same ad again. So with ads, you have complete freedom to do the best you can and no more. And if you do it again next time and you don't get the same result, that's fine.
Yeah, I almost get annoyed when I see the same ads over and over and over again because I've already decided I don't need that product.
And it's probably a bad idea for them to waste the ad space in front of you because you haven't clicked on it, right?
Yes.
So same kind of thing. So there are certainly domains where best you can, change what it is every time, just get it out of the way is a great way to do it. And there are cases where, no, it's just wrong. And obviously when it comes to things that correctness is critical, like the balance of your bank account, best effort calculation of the balance of your bank account is not a good way to go when you can't calculate you. It's better to wait and give you the number than to give you a wrong number.
Yeah, I worked in retail application. I was told by people who understand the domain that people are willing to wait quite a long time after they have decided what to buy, put in the payment information and hit submit. And it can take tens of seconds to complete the charge transaction, and that's acceptable.
So I don't think that's true anymore. It is true that they're willing to wait a lot longer for that than for the other operations. But a lot longer for that today is probably below 10 seconds. In fact, I could say from personal experience that I've run into the situations where I've decided never to shop somewhere again because of that. Specific cases, I'm sitting in a hotel room, I'm booking a flight, I go for the cheap place, you book flights, whatever that is, get everything ready, have the thing, and I go and enter the information, fill it up, and you click and it says, you got the rotating thing and it says, we're processing your order, do not go back, do not hit retry, just wait. Anyway, But after 20 seconds, you start thinking, well, what do I do now? And after a minute, you start thinking, I need to leave the hotel room and check out. What do I do now? And at some point, you get annoyed, close the laptop, don't know if you bought the plane ticket or didn't, don't know if you need to buy it again, whether you spend twice or not, leave. And the actual reaction to that is, I'm not buying from these people again.
Sure.
Right? So I think that it's perfectly acceptable for people today, right now, I think, to wait on the order of 10 seconds for checkout authorization, payment kind of stuff. That's still in the acceptable realm. I think it's going to keep cutting itself down. Mobile behavior is a big reason. The expectation at the mobile level now is much less. Like, for example, in Apple Pay, you don't expect to put your thing there and sit there and stand in front of the counter for 10 seconds while other people are waiting.
Yeah.
Expect roughly 2 to 3 seconds max. But that's the checkout. On the way to checking out, you browse, you put things in the shopping basket, you looked at the shopping basket, you changed your mind 15 times, you did all those things. Those, nobody's waiting 10 seconds. A second is too long for most of those things.
I want to talk a bit more about the garbage collection in relation to this set of problems. We had Monica Beckwith on talking about Java garbage collection, and she talked about their different durations of pauses, and you have some control, you may have some control over when they run. So one technique we covered was if you know that a particular JVM, it needs to do a major collection and compaction, which will take 2 seconds, you can pull that one out of the rotation, experience this 2-second pause while it's not serving requests, and then put it back. Are there other techniques where you can manage the pause behavior?
Well, this is a place where obviously we'll have strong opinions.
Yeah.
And we think it's a terrible way. We think it's a waste of engineering time, or more importantly, it's a great example of the length of people will go to duct tape engineering around a problem that shouldn't have existed. At Azul, we have a really simple solution for this. Those pauses should never have happened, and they don't. And when you take the pauses away, you find that people take away the need to even ask the question of how do I predict when a 2-second pause will happen, so I can take the thing out of rotation and hopefully predict correctly, and then bring it back and deal with the rejoining of a cluster and leaving of a cluster and all the other things. So it's a great example where disruptions of execution that happen for no good reason, except for a garbage collector needs to pause, they both break application behavior, but also force engineers to come up with really complex ways around the problem. So people have absolutely done what you described. Most people don't. Most people do not have the ability to predictively take a node out of a cluster because it is about to have a problem. But sometimes you're able to do that prediction. The thing that makes it hard is it's really hard to tell when a collector is going to pause, if it's going to pause. The approach I've seen some people do is to say, well, empirically, it takes at least an hour between the pauses. So every half hour, I'll take it out and force it to garbage collect to do a full GC and a full pause and bring it back and hope that it'll last another at least half an hour before that happens again. And that tends to work, but tends is a strong point there because garbage collection pauses do not happen because time has elapsed. Garbage collection pauses happen because enough work has been done to cause garbage collection to happen at whatever level, if it's fragmentation or allocation. And for example, if your load just grew by 30%, you're doing 30% more work, chances are that your garbage collections will happen for 30% more frequently. Now you need a predictive model that tells you, based on the current workload, how long I think, at this rate, I'll do at this rate, at that rate. So now you're starting to look at load versus predicted time. And that's not that simple because maybe it depends on the kind of things you do and the size of documents you process and the color of the shirts you sell and who knows what else. And now you need to strongly predict what this machine that is imperfect will do in the future and when the bad thing will happen. So these are not impossible tasks, but they require a lot of voodoo engineering. We believe the approach of just these problems should not be occurring. Garbage collection pauses they belong in the 1990s and shouldn't have made it into this plan.
So the last area I'd like to delve into is trying to engineer a system for bounded latency. How should I be monitoring? What should we be looking at? And what should we be responding to?
So I like to separate the design or architecture from of how to even make the system, put the parts together, from the how to achieve certain latency bounds and behavior once I've got a functional system. And I think the good news is that while the models and the percentiles and others are really hard to predict and actually fairly hard to measure well, the art of capacity planning is usually not one of predicting what you will need, but empirically arriving at the number. So if you think about it, if you've defined your requirements would probably be, we track money correctly, and 1 + 1 is actually 2 for that kind of math. We respond to most people in a snappy manner. That's a median or 90th percentile of a millisecond or two for whatever you do, or 20, or pick a number. We have no more than 90, the 99th percentile is worse, but it's no more than this. The 4.9s are no more than this. Maybe you have a worst case requirement. You come up with what your business, your site, your web store needs.
So you're talking about these are the end user, what the end user should see.
End user experience, the human experience on this site. This is what I want to achieve. And I have a system and it's been built to do it, and the typical operation does fit in that. If the typical operation doesn't, go back to the drawing board, figure out how to shorten your operations. It's not a sizing question at that point. If at idle you still can't meet it, your numbers are off. But if you have a system that could usually do it, but the question is, okay, so how many servers do I need to do that? What I like to tell people is, think of this as in terms of managing misery. You've defined a requirement, and the actual requirement is to not fail, or to only fail your requirements a minimal number of times per day. You could say, these are my requirements. I'm okay if this fails 100 times a day on 100 million operations, but no more. Then the actual question you're asking is, how many machines, how much capacity do I need such that that will be true? The way to establish that is to try. Load it up with 1 machine, with 2 machines, with 10 machines, 20. Grow it to the point. Find through simple searching how many machines are at that edge of being right at the misery point. And then in reality, capacity planning is about tripling that number and going home. So you figure out where it collapses, and the actual answer is, I don't want to be anywhere near that, so give me a lot more and let's be done with it. So capacity planning is about the prevention of crossing the misery line. And that can be very effectively done with empirical techniques rather than theoretical modeling techniques. So take your system, see how it behaves, figure out where the line should be, press it to that line in whatever artificial way you want to do it by constraining the system, and that will establish what you need. Now, if you're fairly small, you would do that in a lab, or you would monitor your systems, compare them to where you are, and probably be conservative about numbers. If you're a very large operation, you can actually play games with saying, I can't do this well in the lab, but I'm willing to experiment on 1% of my users. So I'll take 1% of my users and constrain them to only a certain set of machines and play games with how big that needs to be before I make those 1% miserable. I'm not doing it to everyone. Establish that a little bit and go. And the cool thing about being able to do that, if you're an Amazoner, is that you can often establish your requirements, not just the capacity, by doing that. So how do you know what you want your 99.9% of it to be? Well, we don't actually know, because we don't know what it does to revenue. But what we can do is say, let's take 1% of the people and hurt their 99.9% and see what it does to revenue, so that we can establish a model that says what we want to do for the rest.
Yeah, I believe that's how some of those $1.6 billion per year numbers in the magazine were arrived at. And
what I'm saying about that is I'm willing to bet that that's not the average, or it might have been the average, but then it doesn't tell you much about the relationship. It's the thing that made people not buy is not that the average went up by a number, but that a lot more of them had bad experiences, and that's an outlier statement rather than an average statement.
Enough that it cost them money.
Yeah, or decided not to transact. Most online buying, and this is probably a judgmental thing, but most online buying is discretionary spending. It's spending on a whim. You can reverse your opinion, and anything that makes people reconsider loses money. if they've thought of buying it and it's already in the shopping basket, anything that gives them a chance to change their mind will. And if that thing is you didn't complete the picture, you didn't do that, that took too long, whatever it is, that's only you're never making money by doing that. One-click buttons are the ultimate example of the power of not giving you the opportunity to change your mind.
Yeah.
You click, you can take it back by going and actively finding and canceling something. But the other side where you put it in a shopping basket, but nothing happened until you actually chose to check out, just gave you a long time to think about maybe I don't need this.
I'd like to wrap things up. Gil, do you have a blog, Twitter, any place where people could go follow your account, YouTube channels?
There's a few places. I occasionally blog in a couple places. There's a blog that's called Stuff Gil Says on Blogspot, and then also a latency tip of the day, which is relevant to this subject. You can find me on Twitter at Gil Tene, Giltene. I often post on the Mechanical Sympathy Google group. It's one of my favorite deep technical places to talk. You'll find a lot of postings by me there, and I'm probably a lot more verbose there than in blog entries. And there's probably a lot of recordings of me speaking online, both on YouTube and on FAQ. If you Google for my name and latency, you'll probably find some rants to look at.
We had Martin Thompson on the show about mechanical sympathy. And then Azul, people like to learn more about C4 or other JVM or products at Azul. Where can they do that?
So Azul.com, obviously. We have hopefully the right information on the website. Our flagship product, Zing, which basically eliminates garbage collection pauses completely, is something you can just go to the website and trial yourself and run your application and measure and see how it behaves.
Okay. Gil Tene, thank you so much for speaking to Software Engineering Radio.
Thank you.
For Software Engineering Radio, this has been Robert Blumen.
Getting software to your users quickly and reliably is the most important part of being a software engineer. SnapCI's cloud-based continuous integration and continuous deployment tool lets you set up in minutes with your GitHub account, and within a few clicks will have your first pipeline running. Discover and fix your bugs quickly before pushing to production by setting up stages from simple ones to complex that run automatically when you push your changes. Need more speed? Run tests in parallel with expanded workers and get your feedback fast. Deploy to Heroku, AWS, and more. We even integrate with Slack to give you updates on your builds. Go to snap.ci/softwareradio and build, test, and deploy free for 30 days. SnapCI embodies the lessons that ThoughtWorks has learned from 20 years of software deployment. The same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareradio. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.